Hello, in this video we are going to discuss derivation for array factors. In the previous videos we have seen an array of two isotropic point sources of equal amplitude and same phase in one case, which is called as broadside array, and the second case equal amplitude but opposite phase, which is called as end fire array. Now in this topic, this is topic number 19, we are going to consider an array of n number of isotropic point sources. So from previous video, the concept of two isotropic point sources we are going to extend to n number of isotropic point sources, and these isotropic point sources have equal amplitude and the spacing is made such that they form a linear array. So they have equal spacing between the two elements. So I will show you the diagram first, or the arrangement of linear array of n isotropic point sources of same amplitude. So we have an axis on which all these elements are placed. So this is in the direction of phi equal to 0. There are 6 elements placed at an equal distance. We have considered for simplification the analysis using 6 elements, but in fact there are n number of such elements in this array. Again, in the same way how we did in previous two cases, we are doing a measurement of the field radiated by these point sources at a distant point, that is in the far field. So far away from this array we are going to do the measurement, and these directions, as we have indicated, phi is equal to 0 here, phi is equal to 90 degrees and another angle gamma equal to 0 degrees. So the measurement is done in the direction counterclockwise, in the direction of phi, and as we know, the clockwise direction angle is gamma, because we have taken gamma is equal to 0 here. As this is right angle, this side we get as d cos phi. Adjacent. So the distance between each element is d, it is equal distance. I don't show in all these cases, but as you can see in my notes, I haven't shared these notes, but I will be sharing them along with the video. You can see here the arrangement is done such that it is equal distance. So the aim is to find out the total electric field radiated by this entire array at a large distance in the direction of phi. So the equation for total electric field, I think in my notes I have represented this as E only. It is not E total. So I'll refer E only, not E total, but it is a total electric field radiated by the entire array. So 1 plus, the reason why for the first point source we are taking 1, phase 0, because e to the power 0 is 1, and the phase of this first point source is 0 because it is at the center of the coordinate system. For the second point source, the term of field radiated is e to the power j psi. I'll tell you what is psi angle once I write this equation. For this third source, it is e to the power j 2 psi plus fourth e to the power j 3 psi, and so on. It continues till the nth source, e to the power j n minus 1 psi. So you can see this equation. it is represented as the total electric field radiated. The term, although we write E, is 1 plus e to the power j psi plus e to the power j2 psi plus e to the power j3 psi plus e to the power jn minus 1 psi, because the first element is at the center of the coordinate system. So now let's proceed deriving this equation for finding the total electric field in more detailed way. Now in this equation, psi is representing the total phase difference of fields from adjacent sources. I hope this handwriting is readable. So psi is representing the total phase difference of fields from adjacent sources, and the value of psi is given a very similar way how we computed it in previous derivations. It is given as dr cos phi plus, now this new term delta here represents, I'll come to this delta once I write the equation for dr. As you know, dr is distance in radians, where in the diagram we have represented d, distance between two elements, in meters. So dr, meters to radians, is converted by 2 pi by lambda into d cos phi plus delta. Now delta is another phase difference term that represents the phase difference between the adjacent sources. Are we finding something very similar between this delta term and psi term? This is a total phase difference of field from adjacent source, whereas you can see delta is phase difference. Instead of saying between, I will say phase difference of the adjacent sources. I'll tell you what delta is. Delta is a phase difference between phase difference of source 2 with respect to source 1. It is phase difference of source 3 with respect to 2, and so on. Whereas psi is the total phase difference, that is phase difference of 4 with respect to 1, 3 with respect to 1, 2 with respect to 1. So 1 is at the center at which we are referring to the phase, and delta is representing the phase difference of adjacent sources. So that's the difference between psi and delta. Psi is total phase, delta is the phase difference of adjacent sources only. Now, the amplitude E0 of fields from all these sources are equal, and it is assumed unity. You may be surprised to see there is no amplitude term in this equation. We have represented only phase value. Why? The answer for this is, we can consider amplitude terms E0 here in all these equations, but we have not written this E0 term because the amplitude, or you can say the magnitude of field, is assumed is equal to 1, and it is identical as we have stated in the title. This is a derivation for an array of n isotropic point sources of equal amplitude and equal spacing. The distance between the two elements is same. Now, in order to compute the total field radiated, we need to multiply this equation. This is equation number 1. We will not consider these E0 terms because already we have made them. We have made the term E0 is equal to 1. So we multiplied this equation 1 by e to the power j psi. Multiply equation 1 by term e to the power j psi, which gives e to the power j psi. Here I don't write e total, I write only e, capital E, and e to the power j psi is the term we are multiplying. Next, in place of 1, you can see this equation once again if you want. It is 1 plus e to the power j psi plus e to the power j2 psi and so on. So if we multiply it by e to the power j psi, the first term will become e to the power j psi plus e to the power j2 psi plus e to the power j3 psi, so on up to e to the power jn psi. So you can see the change in the equation here. The term which was the last term, which was e to the power jn minus 1 psi, after multiplication by e to the power j psi term, we got it as e j to the power n psi. This is equation number 2. Okay, fine. Now what we can do is we can subtract equation 2 from equation 1. I think in my notes you may find this as equation number 3, because I have numbered and this equation as equation number 2. So let's say we go as per notes, numbering as per notes, and this is equation number 3. So we subtract equation 3 from equation 1, and all this exercise we are doing in order to find the total electric field. So let's continue by doing this subtraction. So what we get is okay, it's not only subtraction of equation 3 from 1. It is not only subtraction, as I have mentioned here. Subtract equation 3 from equation 1, and it's a continuation in the same term, and divide the result what we get by term 1 minus e to the power j psi. Now this exercise is being done in order to get the trigonometric form of the equation, as we are expecting sine term in this derivation. So the total electric field equation we get is 1 minus e to the power j n psi divided by 1 minus e to the power j psi. You can try doing the subtraction of equation 3 from 1, and then adjust the terms and rewrite this fourth equation as what we are doing here is, since in both the cases, in numerator and denominator, it is 1 minus e to the power j n psi and 1 minus e to the power j psi, we write this second term in numerator and denominator for the first, and since it will become e to the power j n psi minus 1 and e to the power j psi minus 1, and both the minus signs will come and they'll cancel. So this is only a rearrangement, rearrange equation 4 in order to get the proper trigonometric form. So E is equal to e to the power j n psi by 2, we have taken common from numerator, e to the power j n psi by 2, n psi by 2. In the bracket what we get here is, since we write this term first, if you take e to the power j n psi by 2 common from this term, what will remain? E to the power j n psi by 2 minus one term is here, and from 1 we have taken e to the power j n psi by 2. So obviously it will be 1 divided by e to the power j n psi by 2. So 1 divided by e to the power j n psi by 2, in the numerator it will become e to the power minus j n psi by 2. It's a simple adjustment done in order to get this form or this equation in the form of a trigonometric relation. So I hope this will not very difficult. You will understand it easily if you practice it once on a piece of paper. In the denominator also we do a very similar exercise. We take g psi by 2 and in the bracket we represent e j psi by 2 minus e to the power minus j psi by 2. So I hope you understand now. In the numerator and denominator, the form that we are getting can be of a sine form if we manipulate this equation number 5 by dividing the numerator and denominator by divide. I write in brief, in short, numerator and denominator by 2j. Okay, so the term 2j here will result in, if we divide it, the numerator and denominator by 2j, the result that we will get is E is equal to E to the power j n psi by 2 in the numerator, e to the power j psi by 2 in the denominator. This will be our first term, and the second term that we get here is interesting to note. It is sine n psi by 2 divided by sine psi by 2. This is our second term. So the whole purpose of this exercise is to obtain this form, trigonometric form, and in the first term we see a phase angle because it is a ratio of two identical quantities. Of course, the difference is only e to the power j n psi and e to the power j psi. So overall, the meaning of this term, specifically focusing on psi term, is nothing but it is totally a phase, and this phase of the entire first term can be represented as a phase term called zeta. So how can we write this equation now in the new form when we represent it in terms of phase? E equal to, it comes as, the second term we write first because it is representing the magnitude, sine n psi by 2, this is psi, divided by sine psi by 2, and the first entire term, the first entire term is representing the phase zeta. So now we got this equation. We can call this as equation number 6 as per my notes, and this is 7th equation, and the 7th equation we are obtaining is an equation which puts some conditions, because this equation is valid if phase is referred from source 1. If I take you back to the diagram of the array which we have shown, we have made it very clear that there is a phase referred from source 1. 1 is at the center of the coordinate system, so phase is always referred from source number 1. So the 7th equation what we have obtained is valid only if first source is at the center. If we refer to the phase by considering the center point of the array, then we definitely modify equation number 7 in to obtain a different form of it. So that's the reason why 6 elements are referred here. You can see there are total n number of elements. You can say if we take 6 elements, it will be a little odd because we need an odd number here. So let's say we take 5 elements. We take an array of n elements where n is equal to 5. Then third source is the center of array. So if we refer the phase to third source, what is the meaning of referring the source at some particular, referring the phase at some particular point? It is from which source you are doing the measurement. So our new line of measurement or a new angle of measurement will be from source number 3. So we will draw a very similar diagram representing to a distant point from third source, and from here we will measure the angle phi. So in this case, if we refer phase to the center of the array, then definitely equation number 7 modifies and it becomes E is equal to the numerator, which is sine n psi by 2 divided by sine psi by 2. So this is our new equation 8 when phase is referred at the center point of the array. This is one condition you must remember. When we are referring phase to the center, then we get the equation in this form. The value of zeta we will not consider here because we are not referring the first one end of the point source as the phase reference, but we are referring the center. Now you can see clearly from this equation, as these are two sine terms in the numerator and denominator, if psi is 0, then the E equation will definitely in the indeterminate form, because sine 0 and sine 0 we are representing. So 0 divided by 0 is indeterminate form. So there is no question of computing any such value when we have indeterminate form. So it is better in mathematics to consider at this point a very useful concept of limit. We say limit psi is tending to 0. It is not becoming 0, but it is tending to 0. So when with this limit, psi is approaching the value of 0. It is not becoming exactly equal to 0, but when psi is approaching 0, the maximum possible value that can be obtained from this equation, E, would be equal to n. Because then we say the term sine psi by 2 is approaching 0. It has not become 0. If it becomes 0, then it will be 0 divided by 0, which is indeterminate form. It's of no use. But if we say sine 0 is approaching 0, that means it is a small value, and the only observable or only considerable number in this term is n, which is total number of elements. N is total number of elements. So now this equation 9th gives us actually the maximum value of the radiated field by an array of n number of isotropic point sources. So we got the maximum value, we got the actual radiated maximum field. Now the task is to normalize this. And you know how we normalize the field? We normalize the field by dividing the obtained field by its maximum value, and maximum value is n. So the normalized value, what we obtain, and that itself is the maximum value. So we can say E normalized, or as I have written in my notes, it is E max. The maximum value is nothing but the term sine n psi by 2 divided by sine psi by 2 and whole divided by n. So it is 1 upon n. So this is called as an equation for, or an expression for, array factor. Array factor expression is useful in deciding the radiation pattern of two cases which we learned previously, but for more number of elements. In earlier cases we studied it only for two isotropic point sources. The array factor equation helps us in finding radiation pattern when number of elements are more than 2. Say for example n is equal to 6 or n is equal to 10, then we can get two different radiation patterns depending on the arrangement, that is either end-fire array or broadside array. So these two cases we will discuss in the next video. Thank you.